In the last video, we talked about precipitation reactions and acid-base neutralizations. That's one category of reactions, and in this video, we're going to explore the second main category of reactions, which is called redox reactions. Redox is short for reduction and oxidation, so there's two halves of a reaction that's going on here. Let's first look at what oxidation is. Oxidation, as the name kind of implies, was originally thought of as a reaction of anything with oxygen. So, for example, titanium reacting with oxygen would give you this titanium 4 oxide, or iron reacting with oxygen could give you an iron oxide compound. But as people started to look into this more deeply, they realized that reactions with oxygen were just a special case of something that was going on with the substance, and that was that it was losing electrons. So in this first example, titanium is becoming a 4+ charged ion because it's losing 4 electrons. And in the second example that we have here, iron is becoming a 3+ ion because it's losing 3 electrons. So it became clear that oxidation was really a substance losing electrons. It happened in reactions with oxygen, but it happens in other cases as well. Electrons can't be created or destroyed because they're matter, so something else must be gaining those electrons if an oxidation occurs. And that process is what we think of as a reduction in the reduction-oxidation pair. So while titanium oxidizes to 4+ and gives up 4 electrons, the oxygen in this reaction is gaining those 4 electrons to become 2 oxide ions. That's a reduction. Reduction is gaining electrons. These have to happen in pairs. So these are sometimes called redox pairs or redox couples because the whole reaction is both of them happening at the same time. It was pretty easy for us to track where the electrons were going when we saw ions being formed. Like iron becomes a 3+ ion, clearly it has to lose some electrons to become positively charged. Oxygen became a 2- ion, clearly it had to gain some electrons to become negatively charged. But electrons are harder to track if ions aren't formed. Like for example, when water is created from hydrogen and oxygen, there's no ions ever formed. This is a molecular compound made from 2 molecules. It's a little bit harder to track that. So we're going to use a tool called oxidation numbers. And oxidation numbers are just a way to account for electron movement when charge isn't explicit, like it would be with ions. So here are some rules that we can use to assign oxidation numbers, and then we'll talk about what we can do with the oxidation numbers once they've been assigned. The first rule is the oxidation number of a pure element is 0. So in these examples here, sodium and zinc would both have oxidation numbers of 0. But even diatomics, like hydrogen and nitrogen, even though part of a molecule, they also have an oxidation number of 0 because they're not part of a compound, they're just a pure element. The oxidation number of a monatomic ion, so that's an ion that's made from a single atom, is the same as its charge. So sodium 1+, the charge is 1+, the oxidation number is 1+. Sulfur 2- ion, the oxidation number is 2-, just like the charge. We have rules for 3 specific elements as they appear in compounds that will be fairly reliable rules. The first one is really reliable. The oxidation number of fluorine when it's in a compound is always -1. If it's in an ionic compound, of course, its charge is -1 because it's in column 7. But even if it's in a molecular compound, its oxidation number will always be -1. The oxidation number of hydrogen when it's bonded with a nonmetal is always +1. And this is usually how we're going to see hydrogen. If hydrogen happens to be bonded to a metal, then its oxidation number is always -1. We aren't going to see this too often. That's going to be pretty rare in our experience in AP chemistry. The oxidation number of oxygen is usually -2 when it's in compounds. This is almost always how we're going to see it. Now, there are some exceptions. Here's one exception. A peroxide, this is a polyatomic ion. It's 2 oxygens bonded together, and it carries a 2- charge. The oxidation number when oxygen is in this ion is a -1. And then there's another polyatomic ion called superoxide. A superoxide is 2 oxygens that carry a 1- charge, and the oxidation number in that case is a -1/2. Those are very rare. Most of the time when oxygen is in a compound, it's -2. That's a pretty reliable rule. The oxidation numbers added together come up to the charge on the molecule, which would be 0 if it's a molecule, or the ion if it's a polyatomic ion. So let's compare NO2 with N2O. In both cases, oxygen is going to have an oxidation number of -2 because it's in a compound and it's not a superoxide or peroxide. In NO2, 2 minus 2s give you a -4. The molecule is neutral, so the nitrogen's oxidation number has to add to -4 to make 0, which means it must be a +4 oxidation state. In N2O, there's only one oxygen, so the -2 must be balanced by an oxidation number for nitrogen so that 2 nitrogens add up to +2. So each one must be +1. Here's another example, but with polyatomic ions. Again, oxygen in both cases is going to be -2. 3 -2s makes a -6. This ion has to have a 2- charge, so +4 is going to bring that -6 up to -2, so that's the oxidation number on sulfur. In SO4 2-, 4 -2s gives you a -8, so sulfur must be +6 to sum to that ion's charge of 2-. Once you've assigned oxidation numbers, you can identify when the oxidation and reduction are occurring. An increase in oxidation number is an oxidation. A decrease in oxidation number is a reduction. So back to our example, hydrogen and oxygen are both oxidation numbers of 0 because they're uncombined elements. In compounds, oxygen is -2 and hydrogen is +1. Hydrogen got oxidized because its oxidation number went from 0 up to +1. Oxygen got reduced because its oxidation number went from 0 down to -2. Another example, here we have iodine, an uncombined element, that's 0. Here's a monatomic ion. Its charge and oxidation number are going to be the same. Here's oxygen in a compound, -2. -2 twice is -4. MnO2 is a neutral compound, so the manganese is +4 oxidation number. Oxygen is also going to be -2 here. -2 times 4 is -8. This is a 1- ion, so the manganese must be +7 oxidation number. So iodine went from -1 to 0. That's an oxidation. The manganese went from +7 to +4. That's a reduction in oxidation number, so it's a reduction half reaction. Here's another one. Chlorine's an element by itself, that's 0. Here's a chloride ion. Charge and oxidation number are the same, that's a -1. Oxygen here is -2. Hydrogen in compounds, +1 when it's with a nonmetal. -2 and +1 make -1 when you add them together, which is the charge in the ion, so that tells us we did that right. Oxygen's -2. -2 3 times is -6. To get to -1, the charge on the ion, chlorine must be +5. So chlorine both oxidized from 0 to +5 and reduced from 0 to -1. Balancing redox reactions requires a kind of a technique. For one thing, we're going to often get net ionic equations that don't include everything that we need in the reaction. And it's a little bit trickier to keep track of not only atoms, but also electrons. So we'll follow this strategy. The first thing we're going to do is we're going to separate the reaction into a redox pair. Sometimes you need to assign oxidation numbers to tell what's being oxidized and what's being reduced. But sometimes it's pretty obvious. Like in this case, Cr2O7 and Cr3 plus must be a half reaction because you can't make chromium into sulfur or sulfur into chromium. So 1/2 reaction here is going to be Cr2O7 2-, making Cr3 plus. And then the other half reaction is going to be SO2 making HSO4. Okay, so now we separated the reaction into a redox pair, a pair of half reactions. And we don't even really have to know which is the reduction and which is the oxidation at first to proceed. Next, for each half reaction, balanced everything except hydrogen and oxygen. So in the top half reaction, we have 2 chromiums on the left, but only 1 on the right, so we'd have to put a 2 there. And then we have oxygen, which we're not worrying about now. In the second half reaction, we have one sulfur on both sides. That's balanced. We have hydrogen and oxygen, but we're not worried about that at the moment. Next, for each half reaction, we're going to balance oxygen by using water. Since every water molecule has one O in it, however many O's we need on a side of the half reaction, that's how many waters we should add. So on the left-hand side, we have 7 oxygen. On the right-hand side, we don't have any, so we're going to add 7 water. In the second half reaction, we have 2 O's on the left, 4 on the right, so we need 2 more oxygens on the left, so we'll add 2 waters. When we added those waters, of course, we messed up the hydrogen, so we're going to balance hydrogen by adding H pluses on the appropriate side. In the top half reaction here, we have 14 hydrogen atoms on the right. We need 14 on the left, so we're going to add 14 H pluses. In the bottom half reaction, we have 4 H's on the left. We have only 1 on the right, so we're going to add 3 H plus ions on the right. The last step is, now that we have all the atoms balanced, we have to balance charge. We're going to do that by adding electrons where we have to. On the right-hand side, we have no charge. This is 2 3 pluses, so that's 6 plus. On the left-hand side of the top half reaction, we have 2 minus, and we have 14 plus. If we put this together, this is 6 plus on the right and 12 plus on the left. The left needs to be 6 steps more negative, so we're going to add 6 electrons there. Bottom half reaction, this is a -1. This is 3 plus, because there's 3 1 pluses. This is neutral, this is neutral. So overall on the left, this is 0. Overall on the right, we have 2 plus. So the right-hand side needs to be 2 steps more negative. So we're going to add 2 electrons. Now at this point, you should look at where the electrons are. Here I have some electrons on the right and some electrons on the left. You have to have that. If they both end up on the left or both half reactions end up on the right, you messed up someplace, because this is a redox reaction. Something had to be reduced, something had to be oxidized. And at this point, if you weren't paying attention, now you should know that the top half reaction is the reduction half reaction because it gained electrons, and the bottom half reaction is the oxidation half reaction. We lost 2 electrons in the oxidation the way we wrote this, but we gained 6 electrons in the reduction. That can't be, so our coefficients must be off. What we'll do is we're just going to adjust them by multiplying that bottom reaction by 3, and if we do that through the whole reaction, that gets the coefficients right so that the electrons lost and gained are the same. So the second half reaction is going to now be 6 water, 3 SO2, on the other side 3 HSO4 minus, 9 H plus, 6 electrons. And now the electrons lost and gained are the same. Okay, now that we have that all adjusted, we're going to add our half reactions back together. Electrons cancel out, they always do, they should. And now we just add up what's left. So we have 14H plus Cr2O7 2 minus, plus 6H2O, plus 3SO2, makes 2Cr3 plus 7H2O, plus 3HSO4 1 minus, plus 9H plus. And what often happens once you do this, especially if it's a kind of a complicated reaction, is there's stuff you can cancel. Like we have 9H plus on the right, 14H plus on the left. We can get rid of 9 from both sides, and this just becomes a 5. And we have 6 water on the left and 7 on the right, so we can just cancel out 6 waters and have just 1 water on the right. Now this reaction can only occur if we have some H plus ions available. So what we have done is we've balanced this redox reaction assuming that we have an acidic environment. That's not always the case in redox reactions. So now I'm going to show you how to balance a redox reaction in a basic environment. The first step is just do everything the same as if it was in an acidic environment, and then we'll fix it later. So let's do this one. I'm going to first split it up into half reactions, MnO4 minus, making MnO2, and then I minus, making I2. I'm going to balance, manganese is already balanced. I'm going to balance iodine by putting a 2 there. Now I'm going to balance oxygen. I have 4 O's on the left, 2 on the right, so I'm going to have to add 2 water on the right. That gives me 4 H's on the right, and there are none on the left, so 4H plus. And now my total charge on the right is 0. My total charge on the left is 4 minus 1, which is 3. So 3 electrons will bring that to 0, so it matches the right-hand side. There was no oxygen or hydrogen in the second half reaction, so I only have to balance charge. I have 2 negative on the left. I have neutral on the right, so 2 electrons on the right-hand side balances that. Electrons lost and gained have to be the same, so I'll multiply the bottom half reaction by 3 and the top half reaction by 2, so that 6 electrons are lost and 6 are gained. Now I can sum this up. I have, electrons are going to cancel, 8 H plus 2 MnO4 minus plus 6 I minus makes 2 MnO2 plus 4 H2O plus 3 I2s. So here's the part where I make this match that it's happening in a basic environment. I can't have these H pluses, so I'm going to add 8 OH minuses to the left-hand side, and this will basically neutralize to give you 8 water molecules. I can't add 8 OHs to only one side because it's an equation, so I have to do it to the other side too. Now when I add this all up, I have those 8 waters, plus I have everything that I already had. MnO4 minus, 2 of them, plus 6 I minuses, 2 MnO2s on the right, 4 waters, 3 iodides, and now I have this 8 OH minus. And it's often the case that you're going to be able to cancel some waters out from both sides. This is no exception. I can take 4 waters from both sides, and there's my overall balanced equation, adjusted for the fact that it can happen in a basic environment. Okay, let's do a couple practice problems. Stop the video, try and balance this in an acidic environment, and when you start the video, you can watch me do it and see if we agree. First thing I'm going to do is I'm going to separate this into half reactions. As2O3 making AsO4 minus is going to be 1 half reaction, and then the nitrogen substances, NO3 minus going to NO, will be the other half reaction. I have to balance arsenic by putting a 2 here. Nitrogen's already balanced. Now oxygen. I have 8 oxygen on the right. I have 3 on the left. I need 5 more oxygen, so I'm going to add 5 waters on the left. That gives me 10 hydrogens on the left. I don't have any on the right, so I'm going to add 10 H pluses. Now for charge. The left-hand side is 0 charge. The right-hand side I have 10 plus and 6 minus, that's 4 plus, so I need to add 4 electrons to make it neutral like the other side. Second half reaction. I have 3 O's on the left, 1 on the right, so I'm going to add 2 water. That means I'm going to have to add 4 H plus on the left. The right side is neutral. The left side is 4 plus and a minus, that's 3 plus, so that means I'm going to have to add 3 electrons. The electrons lost and gained don't match, so I'm going to have to multiply the bottom half reaction by 4 and the top half reaction by 3. That gives me 15 H2O plus 3 As2O3 plus 16 H plus 4 NO3 minus, making 6 ASO4 minus and 30 H plus 4 NO plus 8 H2O. And then I can clean this up a little bit. I have 16 H plus on the left, 30 on the right, so I can reduce that to a 14, just cancel those 16 out. And I have 8 waters on the right, 15 on the left, so I can reduce that to a 7. So there's your overall answer. Next, balance this in a basic environment. Again, stop the video, try it yourself, and then check your solution. So I'm going to split into half reactions. Aluminum makes AlO2, 1 minus. And NO2 minus makes NH3. Aluminum is balanced already, that's fine. So I'm going to balance oxygen by putting 2 waters on the left. That gives me 4 H pluses on the right to balance the hydrogen. The left-hand side is neutral. The right-hand side is 4 pluses and a minus, so that's 3 plus. So 3 electrons make it neutral to balance the left-hand side. Nitrogen's already balanced in the second half reaction. Oxygen's not. I'll need 2 oxygens on the right, so I'll add 2 H2O. That gives me 4 H's, plus the 3 that were in ammonia. That's 7 H's. So I'll add 7H plus on the left. Now I've got to balance charge. The right side is neutral. 7 plus and a minus makes 6 plus, so I'll have to gain 6 electrons. To make the electron transfer work out, I got to multiply the top half reaction by 2. When I sum this up, I'm going to have 4H2O plus 2Al plus 7H plus NO2 minus makes 2AlO2 minus plus 8H plus NH3 plus 2H2O. And I can take some H2O off both sides, and I can take 7H plus from both sides. This is in a basic environment, so now I have to make my adjustment. I have 1H plus on the right-hand side, so I'm going to add NOH minus. I have to do that over here too. I'll add NOH minus there. And then when I put this together, I have OH minus plus 2H2O plus 2Al plus NO2 minus makes 2AlO2 minus, plus this H plus and OH minus together make it water now, plus NH3. And I can cancel this water away because I have 2 waters on the other side, and there's my overall reaction in a basic environment. Redox reactions come in several different reaction categories. One of them is a reaction called a synthesis reaction. So in a synthesis reaction, you're creating a single substance from 2 or sometimes more reactants. So kind of a format for this would be A plus B makes AB. If the A is sodium and the B is chlorine, sodium chloride is the AB. That's a synthesis reaction. And that's a redox because sodium was 0 and chlorine was also 0, but here there are ions, plus 1, minus 1. A decomposition is like the reverse. This is one single substance that becomes 2 or sometimes more products. And this example of hydrogen peroxide, H2O2, splitting up into water and oxygen, that's a redox reaction that's a decomposition. There's another type of redox reaction called a single replacement. The format for this is AX plus Y makes AY plus X. So this is a kind of a switch. X and Y are switching so that Y is with A after and X is by itself after. So an example of this would be gold chloride and zinc makes a zinc chloride plus gold. So the chlorine is switching partners. It's going from being with the gold to being with the zinc on the other side of the reaction. That's the replacement. This is redox because zinc is 0 oxidation number and gold is 0, but they're both in compounds on their opposite sides, and so they're changing their oxidation state. Another type of redox reaction is called a combustion, and a combustion could be when an element oxidizes by reacting with oxygen to make a single product. This is usually categorized as just a synthesis, but it could also be that a compound oxidizes by reacting with oxygen, and that will produce the oxides of both of the elements that the compound was made of. Reactions in which hydrocarbon-based fuels burn are very good examples of combustion reaction. Here's one. Propane is C3H8. It reacts with oxygen. You get the oxide of carbon, which is carbon dioxide, and the oxide of hydrogen, which is water. Non-redox reactions are also called double replacement reactions. And they have this format AX plus BY makes AY plus BX. So this is like that switching thing, except it's two compounds and they both are switching something. An example of that would be if you had lead nitrate and potassium iodide on the left, and then lead iodide and potassium nitrate on the other side. The iodide and the nitrate are switching partners with each other. This is a precipitation reaction because that's solid forms, and of course that's one of our kinds of non-redox reactions. The other kind is acid-base reactions. These are also known as double displacement reactions or metathesis reactions. And the non-redox reactions that we explored in the last video are the double replacement reactions, acid-base and precipitation reactions.